All right. So, I'm going to start with sort of an outline of the big proof of the Zergel conjecture and a little bit of recap, because there's so many things going on that it's a little confusing, so it's good to get everything in order. So here's an outline recap. And I'm going to use this as an opportunity to assign names to things that I'd like to prove. So S of W, or the Zergel conjecture for W, will be the statement that BW, which, if you recall, was defined to be the unique summand with some property. It wasn't defined in terms of what it was in the Grothendieck group, but that, in fact, in the Grothendieck group, it is the cosjournalistic basis element. So this is a statement which need not be true. It's not true in finite characteristic, but it will be true over R. Okay? And now, it's worth recalling from the exercises in the last lecture that if this is true, then there exists a unique, non-zero, invariant, graded invariant pairing on BW up to scalar. And that it is non-degenerate. Okay? So the point was that it's always true that BW is self-dual, which means that there is some non-degenerate pairing. The fact that BW is HW says that the space of non-zero pairings is in fact one-dimensional. And so that says that any non-zero one is in fact non-degenerate. This is a useful fact. But we're not usually going to use this abstractly defined form. Okay.
You mean something graded, right?
Yes, graded. Graded is always... So we're not going to use this abstract one. We're going to use the induced one coming from it appearing as a summand. Okay? But one thing is certainly true, that if you take the pairing on BSW, the global intersection form, and restrict it to the summand BW, it is non-zero. So why is this? I've said this multiple times, but CBOT and CTOP are both in BW. So I've actually decided to just put this on the exercise sheet. CBOT you can compute for graded dimension reasons. CTOP because there exists a non-degenerate and it's not so bad. Okay. So, in particular, if this is true, then this form is non-degenerate. But a priori, there's no reason this is non-degenerate. Okay. So we have HLW with an underline. So this is going to be the statement. It's a statement about BW. There's a reason to include the underline, and I'll explain. So take BW, take its right quotient, equip it with the form induced from its embedding inside a particular reduced expression. Okay? This is the only sense in which the reduced expression matters. So this barely depends on the reduced expression, but technically it does. And the Lefschetz operator, which I'm going to stop calling L, I'm just going to call it rho, for left multiplication by rho. Where ds of rho is positive for all s. So here's the setup. We have this finite dimensional vector space, self-dual, with a particular form and a Lefschetz operator. This satisfies hard Lefschetz, which meant that the action of rho to the I takes things in degree minus I to things in degree plus I isomorphically. And then, of course, we can also just say HLW, which is HLW for all reduced expressions. Okay, so this is actually what we're going to show. Certainly, if the Zergel conjecture is true, then if one of these holds, then any other one holds. But that's because then these forms are all equal up to scalar. And then we have HRW, which is just the same, except that the above setup has HR. And HRW is HR underline W for all rexes. Yes. Okay, so here are a bunch of things we would like to show. Okay, the thing we actually care about is the Zergel conjecture, but along the way to showing it, we wanted to show that some space was non-degenerate. We show it by showing it's positive definite. Is there any point at which it's too low to write on this board? Is this too low that you can?
So first you need to show, so HLW is HLW underline is
Yeah.
this statement.
Yes.
I would say. And HLW is that statement for all rexes.
Exactly. But you know, modulo SW, these are equivalent. Because all that changes is the form you care about. And if you show that these forms are unique up to scalar, then you actually know they're unique up to positive scalar because C top and C bot pair to a positive number when that doesn't change. That doesn't change. So yeah, maybe I'll say that. Remark that this BSW is sort of already normalized such that the pairing such that the Lefschetz pairing of C bot with itself under rho, and this is in degree minus the length of W, is positive. So this was one of the exercises. Okay, this was an exercise from a couple of days ago. Or maybe yesterday. Okay, so it's not immediately obvious at all, but if you take C bot and you apply rho the right number of times, you get a positive multiple of C top, plus terms that have multiplication by polynomials on the right. So that's, of course, something you would expect if this were true. You need that to be the case. Thankfully it is. So at least that's a start. Now, as discussed, we want to do some sort of induction, right? We want induction. We want to induce using the semi-small object BWBS. And so we want some sort of similar statements for this space. Okay, it's semi-small, so it should have many of the same properties. When WS is bigger than W, this is how we're going to do our induction. But actually, we can ask questions. This is not semi-small when WS is less than W. But we can still say things about it. Okay, so let HL W underline S be, well, you have the following setup. BWBS bar equipped with the form coming from the Bot-Samuelson. And left multiplication by rho. This has HL. Okay, and similarly, HR, WS. Okay. And the point I was just saying, this is semi-small when WS is bigger than W, so there's a chance of this being true. Clearly this fails for WS less than W, because this is not semi-small, so it cannot possibly have hard left jets. This sort of was also on the exercises. And there will be more. This won't be the complete list of useful things that we'll use in our induction, but it's a start. Oh, this eraser's terrible. Excuse me. So let's just remind ourselves how the induction works. So assume S of y, HL of y, HR of y for all things smaller than WS, including, say, W. Okay? So we know that HWHS, I'll write this down again, is HWS plus a bunch of these mu coefficients, which are integers. And we know that these mu coefficients are, in fact, the dimensions of the maps in degree 0 between various spaces. Well, with no negative degree maps. And so we have this pairing. So before I was calling this the local intersection form. And I prefer to call this the local intersection pairing, because it's a pairing between two spaces that we haven't actually, that are isomorphic, but that we haven't actually canonically made isomorphic yet. So we have this thing, which I'll call the local intersection pairing. Okay. And we've seen that it's non-degeneracy, or which is to say that if it has full rank, then the Zergel conjecture of WS is true. Okay? So if full rank, SWS holds. But we'll actually also see a number of things. We'll get there in a sec. In the meantime, let's investigate how to turn this pairing into a form. So both BY and BWBS have canonical, at this point, up to scalar, up to positive scalar, non-degenerate forms. Okay? The former, because we have the Zergel conjecture, and so this has a canonical form, as discussed. The latter, because BW has a canonical form, and you saw in an exercise how to get a form on anything times BS in a canonical way. So these have canonical forms, and so we can use these forms to translate, to give an isomorphism between these two spaces. In sort of the obvious way, so given phi and hom, let's see, which one do I want to do? Y, BW, BS. Its adjoint in hom the other way is defined by the obvious formula that phi of B paired with B prime is B paired with phi dual B prime. This works because they're both non-degenerate. This gives you the identification, allowing you to turn the local intersection pairing into a local intersection form. So the local intersection form on this guy is that if you pair, if you pair two maps from BY to BWBS, and I'm going to write this, YWS, the local intersection form. This is the coefficient of the identity in psi dual composed with phi. Well, this is silly. I mean, the phi dual composed with psi is actually in degree 0, so it is the identity. It's a scalar multiple of the identity. I don't need to say coefficient of the identity, but it's really just the composition of these things. The coefficient of the identity is just a nice way to do this. So now we have the magic embedding theorem. And, the idea to do this was stolen directly from Di Cataldo and Migliorini. But here it is. So we have a map from HOM0 BY BWBS to BWBS right quotient in degree minus the length of y. And this is just evaluated on C bot of BY, and of course take its image. All right? And so I have three statements to make about this. The first is that the image lies inside the primitives under rho in this degree. The second is that it's injective. And the third is that it's an isometry up to positive scalar between this local intersection form and the Lefschetz form. So this is kind of an unraveling of a whole bunch of different things that, roughly speaking, we've already done. It's not so hard. Okay. So first we want to show that it's primitive. So certainly it lies in degree minus the length of y, because that's the degree that C bot is in. So why is it primitive? Well, if we apply rho to the length of y plus 1, or to C bot in by, we get 0 in by bar for dimension reasons. Okay, I mean, this is the absolute lowest. If you apply rho to the length of y, you get the absolute highest. You do it one more time, you're off the charts. Okay, this is clear. Okay. And so from this, it's easy to deduce that rho to the length of y plus 1 and phi of C bot is also 0. This being multiplication on the left, it module map. And taking the right quotient also commutes with any bimodule map. So this is straightforward. So it's primitive. Okay? So the second is going to be a nice application of the light leaf approach to elements. This is sort of the place where we are going to use it. So we know that any map from, say, BSY to BSWS is of the form, it's going to be in some light leaf form. So there's some coefficients, and then you have some light leaf map from y to some z, and then back up to some ws. Okay. Now, up to lower terms, we can assume that this isn't just going to bs of z, but it's actually going to the indecomposable bz. That is, we can just shove the idempotent here. Okay? we can just shove EZ, say the idempotent, which projects to the indecomposable Zirkel bimodule. And this idempotent is the identity plus some lower terms. So all we're doing is changing our basis, if we want to. Okay? So, you know, without loss of generality, it just factors through BZ, not some random reduced expression. Really, light leaves, because of their definition, they weren't even canonical. We never even care what happened modulo lower terms. And modulo lower terms, they might as well be going to the indecomposable BZ. Okay, so I'm actually ignoring the choice of reduced expression there. There's no reason not to. So what we're interested in, though, is a map inside from BY to BWBS. And this would be obtained by taking the exact same expression and then precomposing with the identity, with the idempotent composing to the Zirkel bimodule of Y, and postcomposing with the idempotent projecting to W, and then the identity of BS. Okay? So this is actually what we're looking at, something of this form. But here's where we use magic Hom formulas to make our lives easier. Okay? This is semi-small. Okay, this is not, but this is. Okay? So that means that there does not exist any negative degree maps to or from BZ. All right, remember, by the Hom formula, this thing is a literally integer linear combination of Kazan-Lustig basis elements, because HW was, right? And so is BZ. So by induction, so therefore there are no negative degree maps. That's what we know from the graded orthonormality of the pair. Okay? And there exists a degree 0 map if and only if BZ is a summand of BWBS. Okay? And we can say the exact same thing over here about BY, right? So there is no degree -0 from BY to BZ, and there exists a degree 0 if and only if Y equals Z. And if Y equals Z, it's just the identity. It's the identity. Okay? So how can we possibly get degree 0 here? Right? Well, this thing, this top half, is non-negative degree. And this bottom half is non-negative degree. So to get degree 0, they must both be degree 0. Okay? To get degree 0, both halves are degree 0. Okay? So that means that Z is Y. And this bottom half is the identity. Okay? So phi must just be some sum of coefs of some upside-down light leaf. Here's the idempotent of Y. Here's the idempotent of W, and next to BS. Okay? But lo and behold, we've seen that upside-down light leaves acting on C bottom. The image is actually a basis, which means that it's impossible for such a sum to be 0 on C bot unless the map is itself 0. Okay, so really, all we're unraveling is that upside down light leaves are injective. Okay? But things of this form applied to C bot form a basis, and things of this form with Y on the bottom form a sub-basis. So in particular, phi of C bot equals 0 if and only if phi is 0. There is our injectivity. So that's sort of the trickiest part. Any questions there? The third thing we wanted to show is an isometry, and now we're just going to play around. Okay? So we know that C bot paired with C top and by is 1 by definition. All right? It's induced from BSY. That's how it was defined. And we know that C bot paired with rho to the length of y C bot. Well, this is just going to be some positive multiplication, multiple of B top. So this is some positive number. That was that exercise. So now we compute. Let's pair two things in the local intersection form. The coefficient of the identity in the composition. Sorry, I think I got that backwards. Yes. Psi star composed with phi. And one way to compute the coefficient of the identity is to pair it off. Okay? So this is phi star composed with phi applied to C bot. So this is an endomorphism of y. So this is a scalar multiple of C bot paired with C top. There is a way of finding that coefficient of the identity. Okay? This is just a silly little thing. Okay? Or we, if we prefer, we can do 1 over n of the same thing on the left-hand side and replace the right-hand side with C bot. Okay? But now we use a junction. The 1 over n. Sorry, this is the Lefschetz pairing. Sorry. So what should go here is rho to the length of y C bot. Okay? So here we have rho to the length of y phi C bot. Okay? Phi commutes with rho, so I'm allowed to put rho on the outside. And this is precisely by definition 1 over n phi C bot psi C bot. And n is positive, so this is an isometry up to positive scale. So really, the only computation which actually was important for this was the fact that this is a positive number, this thing on the exercise, which I said was crucial. Everything else is silly and canonical. So that's great. So the corollary of this fact is that if we have HR WS, then that says that the Lefschetz form restricted to the primitive part in degree minus length of y is positive or perhaps negative definite. We know which one actually by just computing some parity. Okay, which means that but because this is a local that the local intersection form is also plus or minus definite, and that was enough to imply. So this is true for all y less than WS. Right, so you actually get every local intersection form at once is embedded into the same space. We show just once that that space is Hadrimon that says that every primitive subspace is positive definite. So every local intersection form is positive definite.
What do you mean by HR W, comma S?
So this is the thing that I said, that if we take BW, BS, with its induced intersection, with its induced pairing from the Bot-Samuelson that it sits inside, that this has Hodge-Riemann. So if we show once and for all that this space right here has Hodge-Riemann, then that will actually show that all at once that every local intersection form is positive definite, which will show that By has the correct multiplicity which implies that what remains after you subtract it has the right size. Okay. So we've reduced our problem to the Hodge-Riemann thing here. Okay, we're going to reduce it still further soon. But what's worth mentioning, of course, is that also the actual indecomposable is a summand of this guy. It's a summand as a bimodule. And therefore, the Lefschetz operator preserves it, because it's just a left multiplication. Okay? It's preserved by rho. And, this is sort of too easy to put on the exercise sheet, that if you take a space which has Hodge-Riemann bilinear relations and restrict to a sub that's preserved by the Hodge-Riemann bilinear relation, that's preserved by the Lefschetz operator, and also it has the right graded dimensions. So the restriction of Hodge-Riemann has HR, then it also has the Hodge-Riemann bilinear relations. So that implies also, so maybe I'll say, so long as the subspace, that if you take the form and restrict it to the subspace, it's non-degenerate, i.e. the graded dimensions are the same, top and bottom, and so forth. But this is true by, we already have the Zergo conjecture for this guy, which has this unique invariant, non-zero form. It's non-degenerate, etc. So this thing has the Hodge-Riemann bilinear relations. So this implies HL for this particular reduced expression and HR for this particular reduced expression. And so then by doing this inductively for everything, you get this statement for all reduced expressions, and so you get, HL WS and HR WS. Okay. Wonderful. So this is sort of step one of the argument, the embedding theorem, which reduces everything from a whole ton of independent local intersection forms to one giant global intersection form on BWBS. Now, we want to get from proving Hodge-Riemann, which is, I guess, harder, to proving Hard-Lefschetz, which is easier. Okay? So we're going to use a deformation argument. Okay? So fix, well, don't fix it. Fix zeta isn't equal to 0, or maybe just arbitrary in the real numbers. Okay? And we're going to let L zeta be the operator on BWBS, which is left multiply by rho on BWBS, and then also middle multiply by rho by zeta times rho. Okay, this is an endomorphism. It's in this nice commutative subring of multiplying by polynomials in different places, so it commutes with the intersection form. So it's actually a Lefschetz operator. Okay. However, what it won't commute with is summand decompositions. Okay? You take an idempotent of this whole thing, a morphism as bimodules, but that doesn't mean it's a morphism also as middle modules. So this guy will no longer commute with some decompositions. It's some weird thing. Okay? So we can also define what we mean by HLWS zeta, which is, the same stuff, so same space, same pairing, but different Lefschetz operator. Okay? We haven't changed the space that we're working over, the right quotient of this. We haven't changed the form we're working on, but we're just changed the Lefschetz operator. And, L0, of course, is our just original left multiplication by row. Okay, so HL0 is what we were originally trying to talk about. Of course, we also have HR. And we can also, investigate when WS is less than W. And now it's not guaranteed to be false. Okay, and in fact, it's going to be true unless zeta is 0. Okay, so this is actually already an exercise that I assigned. It has appeared already that if HLW is true, that this implies HLWS zeta in the specific easy case, actually, when you go down, and zeta is not 0. Okay, so this is already on the exercise sheet. Putting this extra thing in here is enough to sort of split the BS minus 1 and the BS plus 1 and to have a map between them. Not split them, but there's a map between them that sort of interpolates this part with that part. Okay, so this is not going to be directly useful, but will be useful later when we finally do our induction proof. Okay? Sorry I was standing in the way there. So here's my proposition. That if you have HR of W, which we do by induction, presumably, then we can deduce HR of WS zeta for very large zeta. And this is regardless of whether S goes up or down. I don't care. So this is related to one of the exercises you've already done, and I've sort of made it a little bit clearer in an exercise on your current sheet, right? But the main idea is this, okay? L zeta is rho plus, let's say, zeta times m. So m will be this middle multiplication by rho. Okay? Middle mult. Okay? Now, m squared is 0 on BWBS bar. Why? Because we're putting a degree 2 polynomial right there in this slot. We're trying to pull it to the right, right? And when you take a degree 2 polynomial, it'll slide through, creating something a positive degree. Or it'll break with the de Mazur operator, but that's also a positive degree. Okay? So either way, you get 0. Okay? I mean, to the left of one line, you can have linear. To the left of 2 lines, you can have quadratic. To the left of 3 lines, you can have cubic. That's the highest you can get. Okay? So when we're investigating something like L zeta to the k, we have this binomial expansion. But actually, this binomial expansion is easy. It's just this guy to the k, and then k copies of this guy to the k minus 1 times him appearing once. So zeta m. Okay, so this operator we're going to be applying to something in degree minus k is actually, the thing that we sort of really care about, plus this other stuff. Okay? But actually, the whole point of adding zeta is that it's this other stuff which is going to dominate. As zeta goes to infinity, it's only that second term that matters. Okay? And Hodge-Riemann is sort of a continuous thing. If the pairing of v and v is positive, and you fudge the Lefschetz form by a little bit, that's not going to change that fact. Okay? So it's enough to look at this thing here. Okay? It's enough. So it's enough to show that it's enough. Sorry, maybe all right. It's enough to compute the signature of v paired with rho to the k minus 1 m of w for v and w and bw bs in degree minus k. Okay. Now, in the exercises, you already came up with a basis for bw bs degree minus k, or maybe this barred version, so we don't have to worry about multiplication, in terms of bw in degree minus k minus 1 and bw in degree minus k plus 1. Okay? So if you had an element, say, I don't know, an element x in here, then what you would do is you would take x and put a double dot next to it. And you'd get an element, and you'd get an element of, so what I mean by this is put CS next to it, XCS. And that would give you an element of this space. Whereas if you had something here, then you do this. So you do YC1. And that also gives you an element. Okay? And if you actually had an element of X down here, you can, of course, also take L, rho X C1. Because rho X is in this space. Okay? So everything in here is either in the image of L or it's primitive. Okay? So we can look at things of this form, things of this form, and things of this form for Y primitive. We can compute the pairing on that basis and check that its signature agrees with the signature just of this part, which is what you'd expect for the Hodge-Riemann bilinear relations to hold. Okay? So this is one of the exercises. Okay? So compute on a nice basis and the end. Okay? And this really had nothing to do about whether S went up or down. It's just some statement about how CS and C1 work. It's really so we have Hodge-Riemann for very large values of zeta. Okay. And this is wonderful because we have this statement that so if HL of zeta holds for all zeta bigger than or equal to 0, then we have a continuous family of non-degenerate forms that have the same signature. Then HR WS rho zeta, sorry. My zetas look a lot like, there we go. They look a lot like rhos, I'm sorry. Holds for all zeta bigger than or equal to 0. In particular, we get the 0 case, which is what we actually cared about. So actually, the proof of HL for zeta equals 0 and zeta bigger than 0 are actually going to be separate separate. But the whole point of introducing the zeta is so that we could get, is that we only knew HR for zeta really, really big. And it was very hard to just prove it directly. But then if we can show HL for all these things, then we're good. Okay, so we've reduced to showing HL, hard Lefschetz. And remember last time I gave you this proposition where if you can find like this section, you know, this sort of like weak Lefschetz argument, that if you can find another space that already has HR, and you find a degree 1 map that somehow factors the Lefschetz operator in half, then you can deduce HL of one from HR of the other. Okay, and this is going to be the way that we prove HL. Okay, so we want to use this proposition from last time. We want a degree +1 map from BWBS to some lower terms that already have HR. So this is going to be, the way we're going to get this is going to be from a Ruquier complex. But let's do this key observation to understand where this comes from. So L zeta is what? Rho. Let's look at this inside as an endomorphism of the Bott-Samuelson, as opposed to the BSBW thing. This is rho next to a whole bunch of lines with a final S line plus zeta rho. Okay, but we know that we can slide this through. We know that we can relate this in terms of breakings and we can and other polynomials, right? So this is breaking this times the T1 of rho, if T1 is the first thing, plus T1 of rho slid through, plus this term here. And then we break this guy through and repeat. So really what this is it's a linear combination of breaking somewhere with some coefficient plus just multiplication by some polynomial on the right. Some positive degree thing, and this is going to clearly act as 0 in our right quotient. But what's the most important part of this computation? Okay? When WS is bigger than W. This is a reduced expression. And again, from what you computed in the exercises, because it's WS is reduced as a Rex, all these coefficients are positive. Okay, when we break rho through a reduced expression, all the breaking coefficients are positive. This positivity is crucial because our goal is to take this Lefschetz operator and divide it. It's an operator of degree 2.
When you apply this, before you break another one,
Yes. You get dt2 of T1 rho. And then d3 of T2 T1 rho.
but there will be more than one break.
Yes, there's going to be a sum of all the different ways to break.
Okay, that's what you mean by that.
Yes, exactly. Break the first strand, break the second strand, break the third strand, break the final strand S. The coefficient of that's going to have some, this is the only coefficient that this zeta is going to enter into. Okay? But regardless, since everything is always going through a reduced expression, all the breaking coefficients are positive. Wonderful.
There will be multiple breaks also.
There will be many breaks. Many breaks. Many breaks. Every single line will be broken with some coefficient, possibly 0. Okay?
There are no multiple breaks, right?
No, there won't be multiple breaks.
That's right.
Oh, that's what you meant. I'm sorry. No, only one strand is broken at a time because it's a linear map. Rho is linear. All right, this is a map of degree 2, and a break is degree 2. Thank you for I didn't get what the question was. Thank you. Yeah, whenever multiple breaks occur, your life is much, much harder. Because once you break a single strand, what remains need not be a reduced expression. And so then the second break might not be a positive coefficient. Okay, but so long as you're dealing with single breaks, life is good. And so the whole point of having these coefficients be let's call these coefficients zi. Okay, so this is the ith strand which is broken, and we'll call the coefficient zi. Okay, so we claim that zi is bigger than 0. So we can actually divide L zeta in half. Okay? L zeta factors as, so we can take the direct sum of all the just put a dot on one strand maps with coefficient square root of zi. And this is a map from this Bode-Samuelson to a direct sum of a bunch of other Bode-Samuelsons. Maybe I'll say I hat. So we weave out the ith simple reflection to get this new Bode-Samuelson. Okay? So we have a map from this guy to a direct sum of a bunch of other guys. Then we have a map from this direct sum of a bunch of other guys back. From this direct sum back. Degree 1, and the composition is L zeta. And these maps are adjoint to each other under duality. Okay? Remember that a map here and a map back, because these spaces are self-dual, these spaces have an adjunction isomorphism, exactly like we did before. And this adjunction isomorphism is flipping diagrams upside down. We haven't proven that yet, but it's true. So these maps are actually adjoint to each other. And they compose to... this is wonderful. As opposed to keeping track of coefficients on the maps themselves, which ends up being a little bit annoying, I prefer to use just the direct sum of the dot maps with no coefficients, but rescale the various pairings on WSI by this positive rescaling zeta zi. So either the fact that they're adjoint and they compose to L zeta, or the fact that they're adjoint and they may not compose to L zeta, but we've rescaled this pairing, either of these things will guarantee the crucial thing that we wanted, which is that if we take V and W and we apply, let's call this map here, I don't know, sigma, that sigma V paired with sigma W by the Lefschetz form, by the Lefschetz operator, inside this crazy direct sum is equal to the original pairing here. What did I write question mark? I'll write L zeta. Okay? These maps also commute with L zeta. L zeta makes sense here as well on this BSI. And if we've left out the very last strand, then the zeta term is actually multiplying on the far right, and so it can be ignored. Okay? So this is maybe degree minus k, and this is degree minus k plus 1. Okay? But so either by rescaling these forms or by rescaling the maps themselves, you can guarantee this fact, which is the thing that allows us to use the proposition. Okay? So for instance, if we had the Hodge-Riemann bilinear relations on this space, we could deduce Hard-Lifshitz for this. Of course, this isn't what we want at all. This thing is not semi-small. It's about Samuelson. Okay? And we're trying to look at summands inside this. And we know Hodge-Riemann for summands inside this. So we somehow need to cross off all the extraneous terms and ignore them. And this is going to be a homological algebra argument. So this is what we're aiming toward, is to somehow use the proposition for this map. But we need to cross off the extraneous terms. And so explaining how to get to that is going to be the focus of the rest of today's talk, where we introduce Rougier complexes. So this is a good spot for a break if we want one.
Is here.
Perfect. All right.